So we really got into chapter 2 last time. Reminder, chapter 1. I did end up posting just like a little lecture that I did previously on just really the stuff from chapter 1 that you need to know about. It's up on Canvas if you want to watch it. Like I said before, pretty much it's just the kind of scientific method type stuff. So if you want to kind of like a little lecture on that, it's a pretty short video, I think. You could watch it on Canvas. I also posted again the little lecture we did yesterday or the other day up there as well. So in chapter 2, which is really where this class starts, we talked about measurements, or really the idea of measurements, and more so we talked about units and really the importance of units. Remember that whenever you take a measurement, you should always have a number and the unit present. It gives you basically a reference to what that number represents. Remember, if you just have a number, it's pretty much useless. So always in chemistry for sure, always have numbers with units when they're measurements. Also, just a reminder that when you show your work and you do calculations, within the calculation, you want to make sure that you have units in the calculation, throughout the calculation, and also on the answer as well. So very common, people just lay out numbers and just get like an answer at the end, maybe put the units at the end. But you do need to, they want you in this class and all the future chemistry classes that you take to show your work, and part of showing your work is to make sure that you do include those units. We're talking about two types of units. There's the English units or the US units, and then pretty much everybody else uses kind of the metric system. Remember that they sort of came together and came up with kind of a standard unit system that's used for chemistry and other sciences, which is known as the SI system of units. It's really based off of that metric system. And remember, we also use kind of those prefixes, like again, kilo means 10 to the 3, and centi and so forth. So sometimes we have these prefixes, and we talked about how to properly do that. Remember, when you look at something like this, and one of the prefix units, that is how much you have of the base unit. So again, in this case, the base unit is grams on both of them. Kilos the prefix unit, and that is the proper way to do that. Again, it's very common. People kind of do it backwards when they go to do that. We talked about some units of length, which meters, centimeters, kilometers are very common sort of units that are used. We also talked about volume, and milliliters, liters, and cubic centimeters are also very common units that we come across here in chemistry. A reminder that a milliliter is equal to a cubic centimeter. It is a one-to-one relationship between those. The way we get that is like you'll do next week in lab. You'll take like a length times a width times a height measurement. Each of those are length measurements in centimeters, but when you multiply them together, you get something like a cubic centimeter, which is a volume. So that is how we get there, by taking three sort of length measurements, multiply them together, and that will give us a volume. Any questions on any of that stuff we talked about last time? All right, so kind of continuing on here with our units, the next one that we're going to talk about is mass. And mass is the amount of quantity that's present, matter that's present in an object. Matter is really anything that occupies space and has mass. That's pretty much most things. A lot of times we talk about matter in terms of their state, solid, liquid, or gas, and very oftentimes we deal with in chemistry matter, a lot of times transitioning from those different states along the way. The fundamental SI unit of mass is a kilogram, and definitely here in this table, some common mass conversions that we use a lot. I would say 1,000 grams in a kilogram is a conversion we use a lot. And again, you should know, a reminder, as we talked about last time, they expect you pretty much to know everything. Nothing's going to be really given to you, so make sure that you do know these things. Also, there's 1,000 milligrams in 1 gram. So that's also a very common sort of conversion. So those two definitely you should be aware of. You should know those. We use a balance, like you probably maybe saw in lab today, to get the mass of an object. And there is sort of a difference between the two terms of mass and weight. Mass refers to the amount of really matter that's present in an object. Mass is really independent of the force of gravity. So regardless of where you are, if you're here on Earth or you're here, if you're not, I guess you won't be here, if you're on the moon, the mass of, say, of an apple, for example, would be the same in both locations. The weight, on the other hand, is directly related to the force of gravity exerted on it. And the weight, for example, of the apple here on Earth and the weight of the apple on the moon would be different because the force of gravity is different. Just like if you were here or you went to the moon, you would have the same mass because it's all you in both places. But because of the force of gravity, which is, you would have a different weight, which is actually a force. So mass is usually measured in kilograms or grams. Something like weight, oftentimes, are in newtons or pounds, like we weigh ourselves in pounds, is what we refer to sort of as our weight. Very times confusing for people is the process at which we get the mass of an object is we throw it on the balance and we weigh it, right? So it's a process of weighing and stuff like that. So in chemistry and sciences, when we do that process, you're actually getting the mass of the object. You're not getting the weight of the object. And again, mass being independent of the force of gravity, where weight is really a force and affected by the force of gravity, depending on where the object may be. So let's talk about temperature conversions as well. So in chemistry, there's really kind of three temperature scales that we come across. And I would say out of these three, really only one is kind of the one we see the most in chemistry or use the most in chemistry. Really two of the three is kind of what we see here. We have degrees Fahrenheit, which is degrees F. And that is where water boils at 212 degrees Fahrenheit. It freezes at 32 degrees Fahrenheit. That's sort of the temperature scale we use when we like take our temperature or something like that, right? Or the temperature outside is in degrees Fahrenheit. Celsius is more of a metric measurement, while Fahrenheit's more of a US type of measurement. And we have degrees Celsius, and water boils at 100 degrees Celsius, and it freezes at 0 degrees Celsius. For water, those two numbers are definitely numbers that you should know. And I say that because those numbers are used a lot in chemistry as sort of standards of like the boiling point temperature of water or the freezing point temperature of water, which is 0 degrees or 100 degrees. So those are two things that you should definitely know. Now, the last temperature scale is one you might not be too familiar with. It's the absolute temperature scale, later sort of called the Kelvin scale. And Kelvin, capital K, is the symbol for that. And that is where water boils at 373 Kelvin, and it freezes at 273 Kelvin. Now, one of the main differences how we sort of write these temperatures is for Fahrenheit and Celsius, we do include the degree symbol. For Kelvin, we do not. So there is no degree symbol on that one. So if you had something like 373, it would just be 373 Kelvin, no degrees or anything like that. Now, like I said before, out of these three, your Celsius and your Kelvin are going to be the ones that you're going to see the most. Celsius you'll see the most because when you look at your thermometer, maybe you saw it today when you checked in, the scale on your thermometer a lot of times is in Celsius. So it's very common when we do experiments and measure temperatures, say with a thermometer, it's very common in chemistry that we measure it in Celsius. But even more common is, I think I might have mentioned it last time, probably 99.9% of the formulas in chemistry, if it is a temperature and you're going to put it into a formula, Kelvin is the where it needs to be. So we very, very commonly, lots of times, take our temperature from Celsius to Kelvin and put it into the formula. Off the top of my head, there's maybe one or two formulas where we leave it in Celsius, but pretty much 99.9% of the time, if you're doing a problem, it involves temperature, some type of chemistry formula, it should almost be a no-brainer that you need to convert that thing to Kelvin before you put it into the formula. You probably won't go wrong. The other thing that we commonly do is, because we oftentimes have to convert temperature into Kelvin to do problems, a lot of times, though, we want the answer in Celsius. So the second most common temperature kind of conversion is going backwards from Kelvin back to Celsius, while before you put it into the formula, you go from Celsius to Kelvin, and a lot of times you got to put it back into Celsius. Fahrenheit, to be truthfully honest with you, probably outside chapter 2, you're not going to see too much Fahrenheit, but you still need to know about it, but very rarely will sort of Fahrenheit pop up. Here's our differences between boiling and freezing of water. And there's about 180-degree difference in Fahrenheit, about 100 in Kelvin. And this is what accounts for pretty much our ways that we convert from all the different temperature scales, is really the difference in degrees or temperature readings from freezing point of water to boiling point of water. And let's talk about how we do the conversions. Again, a reminder that you are, in addition to everything else, responsible for formulas, including these, how to convert temperature. So these are the 3 sort of temperature conversions that you need to know. If you have the temperature in Celsius and you want Kelvin, which is probably 99% of the time the temperature conversion you're going to do, you're going to take the temperature in Celsius. And at this particular school, they would like you to use the entire number there. You will use 273.15 and add it to it. I would say a lot of people will just use 273, leave the 0.15, but they don't want you to lose that here. So here at this school, you'll see 2 conversions for that. A lot of times people will use this one, which is 273.15. Sometimes in the lab manual, they'll use 273.2, and they're around to like 0.2. So personally, we'll go in this class 273.15. Outside of this school, you might see people just use 273 and leave the 0.15 on the sidelines, but you need to use it here. Now, if you have Kelvin and you want Celsius, you're basically just going to do the opposite. So if you want Celsius, you're going to take the temperature in Kelvin, you're going to minus 273.15. Now, those 2 sort of conversions for temperature, probably the most of the time, those are going to be the ones you're going to do. And out of those 2, like I said earlier, probably converting it from Celsius to Kelvin is going to be the one that you do the most. So definitely commit that to memory for sure. You do need to know the bottom ones as well. So if you want Fahrenheit, you have Celsius, you're going to take 1.8 times the temperature in Celsius plus a 32. That 1.8 is that fraction maybe you learned before. 9/5 is the same thing. So 9/5 is kind of the same idea. If you have Fahrenheit and want Celsius, you'll do the bottom. You'll take the temperature in Fahrenheit. You'll subtract 32. You'll divide by 1.8. So you do need to know all 3 of these. Like I said, probably outside of chapter 2. Most of the time, you're going to be doing the Celsius to Kelvin, and probably Kelvin back to Celsius is probably the one that you're going to do that. If you have Fahrenheit and you want Kelvin, you got to go from Fahrenheit to Celsius, Celsius to Kelvin, and vice versa. If you have Kelvin and want Fahrenheit, you got to go all the way across and go from Kelvin to Celsius, Celsius to Fahrenheit. Any questions? Hold on. Now, we're going to talk about significant figures, obviously, in this chapter, and doing calculation involving significant figures. But temperature conversions in general do not follow strict significant figure rules. And what they follow is basically kind of a general rule that most people will follow. And that's because there's a lot of variation in terms of these formulas. Some people use 273, some people use 273.15, some people use 1.8, 1.80, 9/5. So there's a lot of sort of variations in these formulas depending on which one that you choose. So the general rule when you're just simply doing, I have a value of temperature in 1 unit, and I'm just going to convert that value into another unit of temperature and do nothing else with it, is you make the answer look like the original number. So what do I mean by that? I mean that if your original temperature value that you're converting, say from Celsius to Fahrenheit was a whole number. When you do the conversion, you should convert it to a whole number. If your original temperature went to 1 decimal place and you're just converting, say, from Kelvin to Celsius or whatever it may be, you would take your answer to 1 decimal place. So that is the general rule that we follow when we're doing temperature conversions, and it's specific for just temperature conversions. There's more specific rules for other calculations, but if you're just simply doing a temperature conversion like this, those are the rules that you follow. Any questions on that? All right, so let's try some here. Grab a calculator, make sure. Do each. So the first one here, we got the temperature is 28.5 degrees Celsius, and we want it to Kelvin, so we're going to go from Celsius to Kelvin. So that is our temperature in Kelvin will equal our temperature in Celsius plus 273.15. Here we'll put on our number 28.5 plus 273.15. And if we do all that good stuff there on our calculator there, we're going to get 301.65 Kelvin. Remember, we don't use the degree sign here with Kelvin, so it's just Kelvin. Now, that's what it shows on our calculator. Remember that when you look at your calculator, don't always give it to you to the right digits, sig figs, all that good stuff. So here we would want to look at our original value, and it went to 1 decimal place. So in this case, we would want to go to 1 decimal place, and we would want to round up in this case. So 301.7 Kelvin would be the answer that we're looking for in this case. Any questions on that one there? Okay, looking at the second one, we got Celsius and want degrees Fahrenheit. So our temperature in Fahrenheit is equal to 1.8, temperature in Celsius plus a 32. So we'll go 1.8, 41 plus a 32, and we do all that good stuff there. 105.8 on my calculator, degrees Fahrenheit. Once again here, we're going to look at our original number in the case of temperature to temperature conversions. That is a whole number, which means we do want to round this guy up to 106 degrees Fahrenheit. Any questions on that one there? Lastly here, we got Fahrenheit to Celsius. So our temperature in Celsius is our Fahrenheit minus 32 divided by 1.8. So 160 minus 32 divided by 1.8. Gonna give us on our calculator 71.111, a bunch of ones. It keeps going, I think, degrees Celsius. Once again here, we're gonna look at our original number. That looks like a whole number to me, so 71 degrees Celsius would be our answer in this case. So again, what we're talking about here in terms of how you do your answer is specific for just temperature to temperature conversion. So again, if we're doing some other type of calculation, which we'll talk about later on this chapter, you do sort of follow some little bit different rules than this. Any questions on temperature conversions? So you need to know how to convert all 3 of those temperature scales, go back and forth between them. Again, will not be provided for you, those formulas, so you do need to know them, yeah. We also talked about last time the importance of understanding what those units represent in terms of what type of measurement. So when we see something like 523 Kelvin, we should know when we see Kelvin, that is a temperature unit, right? And if I have 25.36 liters, liters is what type of unit? It is a volume, yep. And 15 meters would be a length, yeah. And kilograms would be a mass, yeah. So again, remember, you want to make sure you understand what they mean, so you don't say like some of the examples I said last time, you know, my volume is like 400 grams or something like that, right? So you want to make sure you got the right sort of units there. All right. So let's talk a little bit about the difference between 2 types of sort of words and observations versus measurements. We have qualitative versus quantitative. Qualitative consists of general sort of observations about a system. So you're doing an experiment, you look at it and go, looks green, looks purple, a solid form. Those are all observations that pretty much do not involve any type of measurement. So a qualitative observation is one that is not involving any type of measurement. If you continue on to Chem 1B, for example, you'll do a bunch of experiments that are known as qualitative analysis. And basically in those experiments, you don't measure out anything. Like if you need a certain volume of something, you go, I don't know, like 20 drops seems good. And you're not really getting any type of numbers or values. You add something, go, oh, a solid formed or a solid disappeared. So these are all things that really don't involve any of measurements. That is very different than quantitative, which is the second one up there. Quantitative is basically all about measurements. It's all about numbers and values and things of that nature. So when you take a measurement, you're doing a quantitative type of measurement. If you were going to weigh out something, you would get an actual value, like 32 grams. If you were going to measure out some water, say in a graduated cylinder, you would use a graduated cylinder, be very careful to get it to the 20 mil line, right, and measure it out. That's quantitatively. If you didn't care, you would just pour into like a beaker around the 20 mil line and go, hey, somewhere in that park is pretty good, and go with more of a qualitative sort of observation. So quantitative comprises of numbers and values. They are basically measurements. They are, as we'll talk about, pretty much where significant figures come from, sort of measured type values. Now, before we get there, let's talk a little bit about numbers and some ways that we represent numbers. And when we have really large numbers and really small numbers, or both really, we often actually use scientific notation to help us write those numbers. So for example, as you can see up there, a gram of hydrogen is about 602.2000, lots of zeros. Number of atoms, or it has a mass of 0.000. I'm tired of reading the zeros at this point, but a heck of a lot of zeros. And obviously, if you were doing some type of calculation with those numbers, there's a very good chance you're going to lose a lot of zeros along the way somewhere, I imagine. So a lot of times when we have really large numbers or small numbers, or just numbers in general, we use scientific notation, and scientific notation is n times 10 to the n. This is a number between 1 and 10. And this up here is positive or negative type number, depending on which way you need to move sort of the decimal point to get to a number between 1 and 10. Now that first one, which is a number between 1 and 10, means that you're good with 1, but you can't go less than 1. So it can't be like point something when you write it in scientific notation. And really, it can't be 10 either. It's got to be a little less than 10. So 9 point something will work. You can't have 10, 20, 100, or anything like that if you're writing proper scientific notation. So we use these to handle large numbers, small numbers, regular numbers, whatever it may be. So for example, if we had 423, although there's no decimal point written there, we would assume it would be down here at the end. If we went one place to the left, that's going to make it 42.3, which is not a number between 1 and 10. We go one more place to the left, that will make it 4.23, which is a number between 1 and 10. And that would give us 4.23 times 10 to the 2. The 2 there on the exponent is how many places you move the decimal point to get to a number between 1 and 10. In this case, it's positive because we moved it to the left. Or if you want to remember a large number, anything above 1 will have a positive exponent. Yeah, so anything that's kind of above 1 will have a positive exponent. If you had 0.02365, by the way, when you write a small number like that, it is very common practice, and you should do that as well. Put the 0 in front of the decimal point so numbers don't run together. We actually need to go to the right here. If I go to the right, that's 0.2. If I go one more place to the right, that is 2.3, which is a number between 1 and 10. And that is 2.365 times 10 to the minus 2. Again, moved it 2 places. Negative because I went to the right, or that number is a small number. Question on that there. Now, when we do write a number in scientific notation, all the numbers before the times 10 part, when you write that number, all these numbers, they're all significant figures. So the question is, do you always have to write your answers and numbers in scientific notation? The answer for me is no, you don't, unless the instructions say to do so. But I will say that at some point when we talk about doing calculations involving significant figures, there is sometimes the only way you can get your answer to the right number of significant figures is to write it in scientific notation. So sometimes that's the only way you can actually write the number correctly with the right number of significant figures. And that's because, for example, if I had 1200 here, there would be no way, for example, if I needed 3 significant figures to write that without scientific notation. So there would be no way to get it in without doing scientific notation to 3 significant figures. I would have to go 1, 2, 3 and write it like that. Now this number has 3 significant figures. Now let's just say I didn't need 3 significant figures, but I needed 2 significant figures. Not a problem for scientific notation because all I have to do is write 1.2 times 10 to the 3. And now my number still has 2 significant figures. I needed 1 significant figure. 1 times 10 to the 3. Now I have 1 significant figure. So you can kind of control when you write a number in scientific notation the amount of significant figures there are based on what you write there, because the one thing that you do know is whenever you write in scientific notation, all the numbers that come before the times 10 part are significant. Now you may be asking, are these kind of like different numbers? So for example, if I took this guy here and wanted to convert it back into sort of positional notation, non-scientific notation, I would need to go 3 places to the right, which will give me 1200 basically when I do that, right? 1, 2, 3 places to the right. If I want to turn this guy back into regular, I need to go 3 places to the right. So 1, 2, 3, put some zeros in there, and I got 1200 as well. So it is the same number, but it has different numbers of significant figures when it is written in scientific notation. It's also really important that if you're asked a question, or if you're just doing a calculation, and sometimes you're asked how many significant figures does this value have, and sometimes you're doing a calculation that involves scientific notation, and you need to know how many it has so you could get to the right answer with the right number of significant figures. It is based on how the number is written in scientific notation. It is not based on putting it back into like decimal form or anything like that. So for example, if you were looking at this number, that would be 1 significant figure without putting it back into non-scientific notation. This would be 2, this would be 3. Sometimes what people do is they will put it back into a number like this guy on the bottom and go, oh, cool, there's like 4 numbers up there, so it's 4. So that's not what you want to do. So if it is written in scientific notation and you need to kind of figure out how many significant figures it has, it is exactly what's before the times 10 part. Before you do anything with it, that is exactly the number of significant figures it has. Any questions on that? All right, so as I mentioned before, n times 10 to the n, it does need to be a number between 1 and 10. 1's okay, 10 is not. And again, negative exponents are smaller numbers, positive ones are larger. Now, more important than being able to write things in scientific notation and go out of scientific notation into sort of regular form there is to be able to punch it into your calculator correctly. And that's where most people struggle. And that is a skill that you do need to know in this chemistry class, every chemistry class that you take. So let's take a moment here and talk about your calculator and scientific notation. So on most people's calculators, you usually have 1 of 3 options. You have an exponent button that looks like this, EE. You have an exponent button that looks like this, EXP. And then some calculators will have a times 10 to the n. And usually on that calculator, you also have like a little will kind of on your calculator next to it on the top right. Usually those guys are like the two-tone calculators. There's like one color in the middle. The outside is kind of a different color. Like, I don't mean to point yours out, but it's something like that one right there, that type of calculator, uh, is those guys on the right. So these are really your exponent buttons. And when you put your number in your calculator, you want to make sure that you're using these buttons and no other button, like everybody's favorite button to use, which is the log button because it says 10 to the x above it. That's going to get you an X on an exam or quiz, so don't use that button for scientific notation. These are the correct ones. A couple of other important buttons are your negative or change the sign button. So on calculators, a plus minus are a subtract buttons that looks like that, not the subtract button. So that is a different button. I would say on most people's calculators, the exponent button is located usually in two locations. Right around here, are right there on the bottom is usually where the exponent buttons are located, kind of towards the bottom right, or right about here. Some people's calculators will have you might need to hit like the shift or second button to find your exponent button. The ones with the will obviously have a will here, and usually the exponent button is also somewhere in this location as well. The change the sign negative is usually also in one or two locations, either down here or bottom right, or somewhere in this kind of area on your calculators, usually where you can find those buttons. So let's talk about how to properly put a number into your calculator. We'll start with these, and then we'll talk about what you need to do if you have that calculator. So let's say we had 3.25 times 10 to the minus 3, and we wanted to properly put this number into our calculator. So this is what you should push. You should go 3.25. You then should hit your exponent button. No multiplication, nothing else. You should hit your exponent button. And what it will most likely look like on your calculator is 3.25. They'll put an E next to it. Or you may have 3.25. It'll pop up a couple of zeros. Or you might have 3.25 times 10 and then pop up a couple of zeros. So one of those options is probably what you're looking at if you just did that. When you hit that exponent button, so when you hit this guy, it actually represents this part of the number here, the times 10 part, which means you don't need to hit the multiplication. You shouldn't. You don't need to do anything weird like inverse log or anything like that. So what is left to do is just to put the rest of the number. It is negative. So we do want to use our negative button, whichever one you have, and 3. And that will go negative 3. That will turn this into a negative 3. That will turn this into a negative 3. And that would be the proper way to punch this into your calculator in scientific notation. Now, if you have the other calculator, kind of the one that has this kind of combination, kind of the two-tone, you basically just got to do the same thing, except in my experience, the way those calculators are programmed, you got to lay up some parentheses around every number that you put in. So how you would do that is you would open a parentheses. You would put 3.25. You would hit your exponent button. And on your calculator, it looks something like this. Parentheses 3.25 will go times 10. And you will have a blinking cursor right up there up on top. At that point, you could just do the rest of it the same way. Your negative button and 3. It then will become 3.25 times 10 to the negative 3. And now your little cursor is going to be right next to the 3. And this is problematic because your cursor is way up on top and not on the bottom. So this is where your wheel comes into play, your little circle that you have. If you hit the right side of the circle, that will bring your little cursor down. You'll have a regular size cursor, and then you could close the parentheses and you'll end up with something that looks like this, and you'll be in good shape. And you just have to do that for everyone. Looks like a lot of steps. I just did each step for you, but obviously you learn how to do it. It'll go really quick, but you do have to do that. The reason usually you have to bring that parentheses down is if you do something like this, 3.25 times 10 to the minus 3, and you just hit the parentheses, you'll have a parentheses up on top. You'll usually get an error on most calculators that have that. So you usually won't want to take that because your parentheses is small rather than large and stuff like that. So if you have that type of calculator, you just got to lay up parentheses around every number that's in scientific notation. If you have a calculator that has the first two buttons, frankly, you could be a little less careful. You could just pop all the numbers in. You don't need parentheses and stuff like that. You'll be in good shape. Any questions on that? All right, let's try a few here, or a couple here, just to make sure. Let's do 4.2 times 10 to the minus 7. We'll divide it by 3.25 times 10 to the 14. See what you get. And then let's do 1.3 times 10 to the minus 6 times 1.798 times 10 to the 9. All right, see what you get. I'll do it as well because I just made it up. We'll hopefully get the same answer. So again, make sure you punch it in like we just talked about each of those numbers. Okay, so let's take a look here. Let's take a look here and see. So I'm going to write out how I would punch it in just to make sure everybody's on the same page. So if we're going to do this, we would go 4.2. We'd hit our exponent button. We would hit our negative button and 7. A little divide button. Put the next number in the same way, 3.25. Exponent button. This is actually a positive exponent, so we do not need the negative here. And we'll go 14 and a little equals. If you have the other calculator, you're going to open a parentheses, going to go 4.2, going to hit your exponent button, going to hit your negative button, going to hit 7, going to do your wheel action, going to close your parentheses, going to do a little divide, open parentheses, 3.25, exponent button, no negative in this case, 14, a little will to bring it back down, and close your parentheses and hit equals. Hopefully one of those two ways we get some answer here. And if we do punch that in to our calculator, we get 1.29230769E on my calculator, 21. So for example, this is the display that I see on my calculator. If your calculator doesn't use E, you may see something like times 10 to the minus 21 there in the far right corner. So in this case, there's a couple of important things. We will round this, and we'll talk why we do this when we talk about significant figures. But basically, this will be rounded to two significant figures, which would be 1.3 times 10 to the minus 21. Now, I would say a lot of people, when they do this and they punch these things into scientific notation on their calculator, or they get an answer in scientific notation, forget all about that thing on the right hand side there, the actual exponent part. So you want to make sure that you do not forget about that when you give your answer. You also want to, when you write your answer, if your calculator gives you scientific notation with an E, you should not write your answer with the E. It should be written as times 10. So don't give your answer, for example, as 1.3 E minus 21. Don't use the E in your answer. It should be written 1.3 times 10 to the minus 21. So don't use that E in your answer when you do that. Quick reason why: when you multiply or divide, your answer should have the same number of significant figures as the one with the least. And in this case, this has 2 sig figs. This one has 3 sig figs. So my answer should have 2 sig figs when it's all said and done. Now, if we look at the bottom one, any questions on that one there? If we look at the bottom one again, we'll punch it in the same way. A little 1.3, a little exponent button, a little negative button, and a 6. Multiplication, 1.798, exponent button, positive 9 there, and an equals. Again, if you have the other calculator with parentheses, 1.3 times 10 to the n, negative 6, circle, arrow, close parentheses. We're going to multiply, open parentheses, 1.798 8, if I didn't miss a number, and R times 10, and a 9. Bring my cursor back down, close the parentheses. In this case here, we will end up with something, maybe. Looks like 2337.4, I believe. Now, again, in this case, my calculator did not give it to me in scientific notation, which is possible. It may give you your answer in scientific notation, may not give it scientific notation. In this case, this guy has 2 significant figures. This guy has how many? 4, yeah. Smallest number of sig figs is 2. So my answer here should end up, because I'm multiplying with 2, which would take me here. And that means that if I wanted scientific notation, I go 1, 2, 3 places. And 2.3 times 10 to the 3 is one way. Or, as we'll talk about, you could go 2300 and label it up that way. One of those two will be correct. And we'll talk about the actual at this point. Any questions on how to make sure you bring your calculator up? We'll figure it out together on yours, but that's usually the most common ways to do it. Once again, you should never use the log button. You should really never use the multiplication button when you're punching something in scientific notation in, unless you're multiplying a number by a number. But to write it in scientific notation or punch it in, you should not use the multiplication button. Any questions on that there? Biggest issue for people is this, like punch it in correctly in your calculator. Yeah, so it's really important to make sure you know how to do it. All right. So why don't you, for each of these, write them in proper scientific notation. So take a moment or two and write these guys. A number between 1 and 10. In this case, I do need to go to the left because that'll make like 56. Obviously, if I go to the right, I got like 5,000 happening, right? So we'll go here. That's not a number between 1 and 10. One more will gives me 5.68762 times 10 to the 2. Now, you may be wondering why I kept all those numbers, and the reason actually does have to do with significant figures. The original number, they are all significant there, so all 6 of those numbers are actually significant. And the way I wrote it there in scientific notation, I got 6 numbers before the times 10 part, which makes it significant as well. If I just wrote this, like 5.7 times 10 to the 2, how many significant figures do I have? I have only 2, which means I lost a bunch of them along the way. And you should never lose significant figures as you go from scientific notation to like decimal form or decimal form backwards. You should always maintain the proper number of significant figures, the same that you had if you're just kind of converting it out. So you want to be careful of that. Here, we do need to go to the right to get to a number between 1 and 10. So 2, 3, 4, 5, and 6, it looks like. 7.72 times 10 to the minus 6. Remember, again, small number less than 1, negative exponent. And again, the number's how many places you moved it to get to a number between 1 and 10. Here, there actually is no decimal point written in the actual number, which does actually make a difference in terms of significant figures. But in terms of scientific notation, we assume that it's at the end, even though it's not written there. And that means that we do need to go 1, 2, 3, and 4 places. Gives us 1.25 times 10 to the 4. Here in this particular case, because there was no decimal point written, as we'll talk about when we get to sig figs, because there's no decimal point written, those zeros actually at the end are not significant, and that's why we dropped them. In this case, the 1, 2, and 5 are actually the only significant figures there, which are 3 significant figures. When we write our number there in scientific notation, we have 3 significant figures. Again, much like the top one where you don't want to lose any zeros, you also don't want to keep zeros. You shouldn't, because if I write it like this, I have how many significant figures now? I now have 5 significant figures. All those would be significant. Again, too many based on the original number that we have. So having more sometimes is just as bad sometimes in chemistry as having less. Yeah. So sometimes people think I just add a couple extra zeros, makes it look more scientific-y and all that good stuff, right? So you don't just want to do that. You want to maintain the same number of sig figs. And obviously we will talk about the rules a little bit later on. Here we're just going to head one place over, 1.35 times 10 to the minus 1 in this particular case. Any questions on any of those there? So again, you do need to be able to write things in scientific notation. You be able to go for scientific notation backwards. And probably more important than all that is you need to be able to punch in your calculator correctly. Yeah, and all that kind of things. Any questions? By the way, when you do punch in your calculator, if you find yourself at some point looking at your answer and it looks really, really close, like the front part looks good, but the exponent part is just like off by 1 or something like that, it most likely is how you're punching it into your calculator is why you're getting really close and just slightly off and stuff like that. All right. So let's talk about uncertainty in measurements and how we kind of get significant figures. So a measurement, as we talked about, is a quantitative observation which involves numbers and values. No matter what you do, there is always going to be some type of uncertainty in a measurement. So the degree of uncertainty in your measurement will depend on what piece of equipment you're using, the scale that's on there. So when we take a measurement, it's always really important, whether you're using a ruler, whether you're using a graduated cylinder, a burette, whatever it may be, that you actually look at the piece of equipment and figure out what the scale basically means. So let us take a look at an example of this. So let's say we had a ruler. We'll call these centimeters. And let's say we were going to measure an arrow somewhere like that. So whenever you look at any type of measuring piece of equipment, there's always going to be some type of uncertainty, some type of guessing basically, or estimation that's going to occur when you take a measurement. So when you look at any scale, there's usually two types of numbers. I call them usually, and a lot of people call them kind of the large markings. And there's obviously the small markings. The large markings are the ones that actually have numbers usually next to them. So in this case, the 1 and the 2 are large markings. And the difference between two of the large markings here, 1 and 2, is a difference of 1 centimeter, right? So each of the large markings there basically represents 1 centimeter on this scale. Now, if we look at it, we also will typically see small markings. And small markings are the ones that typically do not have numbers on them. So they're actually the markings that you find between the large markings. So the ones that actually have numbers, then you have the little markings between them. Those are the small markings. And we want to count how many we have of those. And it's important when you count that you do count correctly. And to do that correctly, you start counting at the just past the last large marking. So for example, here we have a large marking at 1. So we would start counting here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we would stop at the very next large marking. So we basically have 10 markings between a total of 1 centimeter. That means each of the smaller markings represents how much? Each of the smaller markings represents 0.1 centimeters. If you're not sure, take the large marking divided by 10, right? And you'll get there to your 0.1 centimeters. That means this first marking here, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 10, basically, if we go all the way across. Now, once you've figured out what the large markings represent, what the small markings represent, you're ready to actually take your measurement. So there should always be numbers when you take a measurement, which are referred to as certain numbers. And those are numbers that no matter who takes a look at it, everybody should agree. So everybody should agree that when they take a look at my ruler here, my arrow is at least 1.4. There should be like no doubt about it. It's definitely 1.4. And those numbers should always be recorded. So these are all the certain numbers. So when you're taking a measurement, you should always record all the certain numbers. Now, this is where we come into our uncertainty in our measurement. And the uncertainty is, I could clearly see my arrow is not 1.4, and it's not exactly 1.5. This is where the guessing comes into play, or the estimation basically comes into play. So we'll just kind of draw it there. Now, when I look at that and I look between those two, I may think, yeah, it's kind of halfway between the 2 points there. So I will record a 5, and obviously my units of centimeters. This would be what is known as the first uncertain number. And it's uncertain because somebody else may look at it and go, I think it's a little bit more than half. Maybe it's like a 6 or a 7. Somebody else may look at it and go, I think it's maybe a little less than a half. Maybe it's, like a 4 or something there at the end. So there's some uncertainty in that measurement in that last digit. Whenever you take a proper measurement, you should always record all the certain numbers plus the first uncertain number. And when you do that, that is our friends' significant figures. Which means in this case, this number has how many significant figures? Yeah, there's 3 numbers there. I would go with that. 3 significant figures. The uncertain number being the 5 in this case. And basically what you're saying is, I think it's 1.45. But hey, maybe it's like 1.46. Maybe it's like 1.44. It's somewhere in that ballpark of that last number is where that uncertainty lies. But it's somewhere in that area. Any questions on that? Now, it does depend on the piece of equipment that you're using. So let's just say you had like a graduated cylinder, really badly drawn here. Probably why I failed art 10 times, but we'll go with it. We got, it's only 5, that's all right. So that's 10 milliliters. $20 milliliters. We'll throw some liquid in there. So when we do measure a liquid in, say, like a glass container, like water in a glass container, we typically will see the curvature of the liquid, dramatically drawn there as a U. And that is what's known as the meniscus. And what happens is the interaction between the liquid, like water, and the glass, they interact with each other, and the attractive forces between the liquid and the glass are stronger than the attractive forces between the liquid and itself. And through capillary action, where it touches the glass, it starts to rise up the side of the container, creating this U. And when we have this type of meniscus, which is probably 99% of the time the way your meniscus will look, we always read from the bottom. If I could draw a straight line really badly there. We read from the bottom of the meniscus. Try that again. I invented erasers, I suppose. There we go. Semi better. We always want to read from the bottom of the meniscus, and that's because the liquid there is not touching the side. It's not affected by that capillary action. So without that attractive forces, the real volume would be back down like it is in the middle. So that's why we read from the bottom of the meniscus here in the middle of it where it's not interacting. To be truthfully honest with you, 99% of the time, that is what your meniscus looks like. There are certain things like mercury, for example, goes the other way. Actually, we'll make a meniscus that kind of goes upwards. In this case, you would actually read from the top of the meniscus in the case of mercury. And that's because in the case of mercury, it's actually attracted to itself more than it is to the container. So it actually comes down on itself and makes kind of the upwards one. Again, almost 100% of the time, that's what your meniscus is going to look like, kind of the U shape. And you should read it from the bottom of the meniscus. We're going to do our same thing here. We're going to go large numbers. Large markings here is, in this case, 20 and 10. That is a difference of 10 milliliters. When we subtract those two, 20 minus 10 is 10. We start counting our smaller markings here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we got 10 smaller markings. So if you're not sure, 10 smaller markings, divide that by 10. That means each of the smaller markings here represents 1 milliliter, right? 10 divided by 10 is 1. That would put this as 11, 12, 13, 14, 15, 16, 17, 18, and 19. If I draw a little bottom of the meniscus line, we could see if we take our reading, everybody should agree it's at least 14 in this case. Again, not exactly 14, but let's just say we think it's just slightly above half. So we will record 6 milliliters in this case. These are all of our certain numbers. This is our first uncertain number. And that means in this case, this guy would have how many significant figures? 3. Uncertain number again, in this case, the 6. Any questions on that there? Now, it really does depend on the piece of equipment you're using, and you should always look at the scale. So, for example, if I had another sort of graduated cylinder action, bad quality control at the factory there. All right, we got it. Lay me up something right about there. So now when I look at this, I got my large markings here, 20 and 10 milliliters. So that's going to be 10 milliliter difference. If I count my markings in this case between them, that is 1, 2, 3, 4, and 5 markings. Now in this particular case, each of the small markings represents how much? 10 divided by 5 is 2 milliliters, right? So each of these smaller markings in this case represents 2 milliliters. This would be 12, 14, 16, and 18. Now when I take my measurement, I am between 14 and 16. What number comes between 14 and 16? It is 15, right? And this would be the proper number here to record. This would have how many significant figures, by the way? It would have 2 significant figures, yeah? The uncertain number would be which one? Our estimated number would be? It would be the 5 is the estimated digit in this case. The reason for that is between 14 and 16, if we just blew up that part of it, there's no way to know where 14 ends, right? And 15 starts. It's not enough room between. It's too much distance between those two numbers. So the best we could do in this case is actually go to the whole number, and we'd actually have 2 significant figures in this particular case. So it is really important to look at the scale. It may be different depending on the piece of equipment that you're using. Any questions on that? Now, in general, this is a good example of something that you can't do this, but in general, you usually could go to one more place to the right of the smallest marking. So you can usually go one more place to the right of the smallest marking. This is an example where you can't do that. This is an example you could do that. Our smallest marking is the whole number. We're able to go one more place to the right to the first decimal place. We look at our first measurement. Our smallest marking was the first decimal place. We're able to go one more place to the right, and that is where we recorded our number. First off, any questions on how to properly take a measurement here? Now, they also like you at the school to include what they sometimes call the precision or the uncertainty in your measurements. And it can help you if you're really not sure how far you should take the reading to, but you are fairly confident in what each of the smallest markings represent. So if you look at something and go, I'm fairly confident that it represents 0.1 centimeters, each of the smallest markings, you could actually figure out how far you could take the reading to by simply taking, for example, here, our smallest markings was 0.1 centimeters. You could divide it by 2. And that will give you plus or minus 0.05 centimeters. That is how many decimal places? 2 decimal places, yes? And that is how far we took our reading, to 2 decimal places. So it will tell you how far to take the reading. If you're for sure about the smallest marking, all you have to do is divide it by 2, and it'll tell you how far you should take that reading to. And they will oftentimes want you, probably especially in lab, if you were going to give this as your measurement, they would probably want you to write 1.45 centimeters plus or minus 0.05 centimeters, including the uncertainty in the measurement. So in lab, they most likely will want you to write it like that with the uncertainty. You get it by dividing the smallest marking by 2, and that will give you plus or minus the uncertainty. We could do that with all of our examples here if we went to this one, where the smallest marking was 1 milliliter. We divide it by 2, that gives us plus or minus 0.5 milliliters. That is 1 decimal place. That's exactly where we took the reading to, 1 decimal place. So again, it will tell you how far to take the reading, and you would record something like 14.6 milliliters plus or minus 0.5 milliliters. Question on that there. By the way, it even works for the weird one we did at the end. We come here, our smallest marking is 2 milliliters. We could divide it by 2, gives us plus or minus 1 milliliter. That's a whole number. That's exactly where we took our reading to, the whole number. And this would be 15 milliliters plus or minus 1 milliliter in this particular case. Question on how to include the uncertainty or precision in the measurement there. Basically, smallest marking divided by 2 gives you the plus or minus part of what you should include. But more importantly, it'll also give you how far you should take the real reading too. Any questions on that there? Definitely something they want you to include in lab measurements. Every time in a lab that you're taking any type of measurement, they typically do want you to include the plus or minus 0.5 or plus or minus 0.05 with it. So make sure you get in the habit of doing that throughout this class and the rest of the classes here at Saddleback. They'd like you to include that in your measurements when you're doing lab. Any questions on how to do that? Let's talk about then another very common thing that people, well, frankly, screw up on. So let's just call it what they did. They mess up on. Well, take the ruler like we used in the very first example. So if I redraw that exact same ruler here, so we got our exact same ruler we used on the very first one that we looked at there. And I'm going to draw my arrow dead on that marking right there. So again, just like we saw before, our large marking is going to represent 1 centimeter. We again have our 0.1 for our small markings. Let me just kind of fill those guys in like we had before. So clearly, if I look at it, I'm dead on this marking right here, which is 1.4. So I record 1.4 centimeters. I record 1.40 centimeters. I record 1.4000000000 centimeters. Doesn't matter which one I record. So let's see if it does. First off, I'm going to say too many zeros. As I talked about earlier, too many zeros, not good. I'll explain why in just a second. Let's take a look at each of these measurements, see if there really is sort of a difference. Let's start with what we know. If we take this guy here, how many significant figures are there? There are 2 significant figures, right? So there's 2 significant figures. The uncertain digit in this number, estimation digit is, it is the 4, yeah? So that is our uncertain digit. So when we look at this measurement, we're basically saying, for example, I think it's 1.4 centimeters, but maybe it's like 1.5, maybe it's 1.3, right? Because the estimated digit in this case is back here. If we look at our scale here on the actual piece of equipment we're using to measure, 1.3 to 1.5, is that a lot of error there? That's like a lot of, I'm just going to throw the dart at the side of the wall and hope I hit something, right? So there's a lot of error with that, right? And if we look at the next number, this guy has how many significant figures? It does have 3 significant figures. Which one is the uncertain one here? It is the 0 is the uncertain one here. So when we look at this, we're saying, hey, I think it's 1.40 centimeters, but maybe it's 1.41, It's like 1.39. So when we look at that, we're looking at pretty much in that ballpark, right? Where the red is that a lot of uncertainty? That is not a lot of uncertainty, right? Which one is the better measurement? 1.40, right? It is because on this particular scale, if I take my smallest marking, and don't erase it, if I take my smallest marking divided by 2, gives me plus or minus 0.05 centimeters, which means my answer should go to 2 decimal places. Yeah. So the correct measurement here should be 1.40 centimeters plus or minus 0.05 centimeters. Because even though they're all 1.4, by lopping off that 0, we made that measurement pretty crappy, right? There's a big area of uncertainty. It's like we shouldn't have that much uncertainty based on the piece of equipment we're using. We have a piece of equipment that gives us really what we have in the middle, this much uncertainty. But by you taking off that 0, you just gave that equipment this much uncertainty, which gives you a crappy measurement, which means that when you go do a calculation with this measurement, because it's the worst measurement, your calculation is not going to be off because you're not. So sometimes people think it doesn't really, it's like right on the line. I don't need to still take it to the right number of significant figures when I take that measurement. You do, you need to add the 0. And would I cross out the one on the right? This is the other sort of extreme. This would tell me that this measurement, if I did the one on the right, is way better than I could ever do on that scale, right? That uncertainty would be way over here, yeah? And there's no way in heck on that scale that I could take that reading all the way out there. So adding extra zeros when you shouldn't is telling somebody that the measurement you took is way better than it actually should have been. So it's not good to go in either of those directions. It's good to go to the right spot of where you can take those readings to, which is why you want to make sure you look at the scale, figure out how far you could go by simply taking the smallest marking divided by 2, basically will tell you how far you could take it. And if you need to add the 0 to maintain the proper number of significant figures, you need to do so, because if you do that and get rid of it, you're making your measurement a lot worse than it actually should be. Any questions on that? Yeah. Yeah.
This smaller mark, which is 4 divided that by 2.
Yeah.
And then 1.6 and 1.2 as the reading.
Yeah, no, when we talk about dividing the smallest marking, it's not the particular individual small marking where the actual thing you're measuring is. It's the smallest marking on the scale. So on this scale, the smallest marking on the scale is 0.1, and that's why we would divide that by 2 to get it. Yeah, so it's not specifically, where it's at. Most people, even though they do it at this school, divided by 2, you get like 0.5 or 0.05 plus or minus. Most people consider the uncertainty in that last digit like plus or minus 1 above or below. So somewhere in that ballpark. Because really, I mean, if you're missing it by like 0.05 this way, you're kind of not making a great measurement anyway. So I mean, you should be able to kind of zero in on it. So most people consider sort of it as plus or minus 1 of that uncertain digit. But here they do it by 2, so you end up with like a 5 at the end of the number. So technically speaking, it could have that kind of flexibility in that last digit that's uncertain. By the way, we're talking about sig figs here in measurements. Just so you know, we'll talk more about it later. It is not always the last digit that's written in a measurement that is the uncertain digit, but it is always the last significant figure that's written is always the last one. So what do I mean by that? I mean by that, just to finish up on that 1200 number that we looked at. In this case, these zeros are not significant. This one is significant. So the 2 here would actually be our uncertain number because this has 2 significant figures. So it's not 100% always the last number there. Sometimes people get in a habit when they're asked a question, what's the estimated digit or the uncertain digit? They always go for the last number. A lot of times it is the last number, but it's not always the last number, but it should always be the last significant figure that's written there. Any questions on it out there? All right, we're laid up there.